Panikkasseerysu. Are you still with us?
Oh yes, I just realized that.
Yeah, we can't hear you.
Oh, can you hear me now?
It's not muted.
Are you?
I am.
I have unmuted myself. Oh,
No, we can hear you. It's all good.
Oh, okay, good.
Yes.
So let me figure this situation out. The share screen. Okay. So while this is happening, I just want to say thank you for organizing this virtual session, and I'm very excited to actually share my research. Can you see my slides?
Yes.
All right. Okay. Hi, my name is Rutvika, and I'm going to be talking about using a foraging approach to analyze infant and caregiver vocal behavior. Oh boy, this is not working. Oh, it worked. So we know that human babies' vocalizing abilities grow tremendously during their first year, while cries and short, quiet sounds like this. Oh boy. Could you guys hear that?
Yes, yes, we could hear it.
Okay, good. Just wanted to make sure that, because I do have some sounds playing in this talk. So cries and very short, quiet sounds like this dominate early utterances or vocalizations, which are two terms I would use interchangeably. And then babies start producing a wider range of vocalization types with variations in pitch and amplitude by about 3 months, and at 7 months, infant speech has already advanced to babbling, which sounds like this. And it has well-timed vowel consonant variations. Part of this increase in vocalization repertoire is due to anatomical changes and the brain maturing. However, even newborn babies' vocal tracts can produce a wide range of sounds. So the really dramatic changes in infants' vocalizations over the first year are believed mostly due to learning. Computational models of infant vocal learning have shown that some combination of social rewards, imitation of adult speech, and exploratory processes can result in the vocal learning we see in human infancy. And so we know that social responses provided by adult caregivers are very important in shaping infant vocal learning. In fact, we can actually think of this as a process where the infant is moving around in some space and interacting with adult responses such that the infant's trajectory in the space is modified by adult responses. And physicists know a lot about such search processes or foraging processes. And here is an example of a 2D random walk search, just for context. So we decided to look at the dynamics of socially guided vocal exploration over the course of the day by both infants and their adult caregivers using a foraging approach. And I think I've made a good case for why we want to look at infant vocal exploration, but the question is, why do we also want to look at adult vocal behavior in this context? And that is because we also know that adult caregivers engage in similar vocal behaviors as infants when interacting with them. So in the study, we look at the vocal behavior of infants and their adult caregivers as exploration or movement in acoustic space, which is an approach that has not previously been used in the field. And our hope is that it will enable comparison of this kind of behavior to other well-understood foraging behaviors, such as animal movements and human cognitive processes. So far, we have a hypothesis that adult caregivers and infants act as interacting foraging agents. The next question is, how can we test this based on our understanding of foraging theory? One thing we could do is to test whether receiving a response from a caregiver is associated with greater degrees of social responding by the infant, and vice versa for the adult, or whether a response results in more focused exploration in that region of the acoustic space. And I'm going to flesh out the idea of this acoustic space later in the talk. And we also investigate whether these patterns of movement change over the course of the first year, because we already know that infant vocalization behavior changes a lot over the course of the first 18 months. So now let's talk about what kind of data we're using. We use day-long naturalistic recordings of infant vocalizations and the acoustic environment provided by their adult caregivers, which is automatically recorded and processed by the Lena Pro system. The LENA system consists of a small audio recorder, which is placed in the chest pocket of a cloth vest that the baby can wear, as shown on the top left corner. And the associated LENA Pro software automatically segments each audio recording into little pieces like this. And then it labels each piece, each tiny vocalization as shown here. The data we get include the speaker label, CHNSB for child speech related, MAN and FAN for male and female adult, respectively, the start and end times of the vocalization, the mean pitch or frequency of the vocalization, and the amplitude or loudness. So we had data from a total of 17 participants, where 15 participants were recorded at 3, 6, 9, and 18 months, and the other 2 were recorded more frequently between 1 to 13 months. So with this data, we defined the relevant acoustic space by the amplitude and the log mean pitch at the utterance level. And while this space does not reflect the complete set of acoustic features that are relevant to human vocal communication, we have chosen to use this because they are, for one, automatically measurable, and 2, they are relevant dimensions for adult vocalizations, as well as most vocalizations produced by infants in the age range that we look at here. And we use log pitch because the perception of pitch is more accurately represented on the log scale. We define distance in the acoustic space as Euclidean, and we find that this distance, or the step size in this acoustic space, and the time taken to make that step are positively correlated for both infants and adults, and which validates the use of this measure as a distance. And this is just more proof of concept, where we show trajectories in the acoustic space for a 3-month-old infant plotted in yellow and their adult caregiver vocal environment, which is plotted in blue on the left, and on the right, we have foraging patterns of spider monkeys on the right, and we can see that they look similar. So how do we quantify interaction between adult caregivers and infants? To do this, we look at the time course of infant and adult vocalizations. And if, for example, speaker type A for adult vocalizes within 1 second or less after the end of the previous infant type vocalization, then a response is received. And if there is no adult type within 1 second or less after an infant type, then a response is not received. And finally, to avoid temporally spaced out pseudo responses from being counted, if 2 adult types or 2 infant types occur within 1 second of each other without an intervening type of the other kind, the response is not applicable. Based on this criteria, we can categorize intervocalization step sizes, or the distance between the I and the I+1 sound, in pitch, amplitude, distance in acoustic space, and time. Do note that the temporal distance is quantified as the time between the end of the last sound and the start of the next sound. All steps that have a response received between the initial and final points get grouped in the with response, or WR category, while all steps that have a no response between the initial and final points get grouped in the without response, or WR category. And finally, steps with an intervening not applicable response type are discarded from the analyses. So now we fit the distribution of step sizes and different features to one of 4 standard probability distribution types: normal, log normal, exponential, and Pareto, which the last one is a kind of power law distribution. And we determine the best fit using Okaige's information criterion, which is an information theoretic measure that quantifies information loss when data is fitted to a set of predefined distributions using maximum likelihood estimations. So here we show, in the bigger panel, we show with response acoustic step size data from an infant at age 3 months fitted to a log normal distribution. We then compute the median and 90th percentile values of each distribution based on the data, as well as the fit parameters. So for the example shown here, that would be the expected value and standard deviation of the variable's natural logarithm. We found that the with response and without response step sizes in both time and space were largely log normally distributed for infants, and that step sizes in acoustic space was distributed log normally for adults. On the other hand, intervocalization intervals for adults were largely power law distributed, which indicates that vocal foraging may not be a Levy process, as has been found in several other contexts. When we compare distribution fits and median and 90th percentile values of distributions, we found that adults take larger steps in the acoustic space after receiving an infant response, which indicates a more diffuse exploration, which could be a prompt for infants to diversify their own exploration. And we did do statistical analysis using linear mixed effects models on the median and 90th percentile values of the distributions, as well as the best fit parameters to reach these conclusions. I just didn't want to put all those tables in here. As for the intervocalization step sizes, they decreased for both adults and infants after receiving a response from the other speaker type, which means that once a response was received, both speakers vocalized more often, which in turn indicates a more focused bout of exploration. This also supports our hypothesis that infants and adults forage for social responses, and also fits well with a large body of research on naturalistic infant caregiver vocal interaction that shows bidirectional coupling in these interactions. With infant age, we found that adults and infants take larger steps in the acoustic space, with stronger support for adults taking larger steps, which could indicate increased presence of varied exploration as the infant gets older. And finally, with infant age, we found that adult vocalizations became temporally sparser to perhaps encourage more independent exploration. In conclusion, this study is a novel application of foraging theory to characterize infant caregiver vocal interactions by assessing exploration, vocal exploration in terms of patterns of movement in an acoustic space. And we found support for a hypothesis that infants and adult caregivers act as interacting foraging agents in search for social responses. Our hope is that this will allow this kind of behavior to be compared to other well-understood foraging behaviors. And in the future, we plan to construct a Bayesian computational model to simulate infant caregiver vocal foraging behavior to really understand what mechanisms underlie this kind of behavior. And perhaps more importantly, the study can have applications in detecting atypical learning patterns early on to facilitate early interventions. So we're very excited about this work. I would like to thank all our funding sources and all of the people who worked on this paper. I can take any questions now.
Thank you. Okay, we have a question from Adria, who is now unmuted.
Okay, let me, okay.
Hi. Hi. It's an interesting concept, foraging for social interactions, when fundamentally the social interactions comes from these two interacting. So it's not really a separate thing that they can find. Is that, am I right? Am I misunderstanding?
We're sort of thinking of it in terms of these responses can be localized in certain regions of the acoustic space, and that's sort of, those locations are where the agents are sort of searching for.
So that, like, you find, do the partners explore different types of vocal interaction? Is that what you mean?
Sorry, could you repeat that? You broke up a little bit. I'm really sorry.
Sorry. So I'm curious. These interactions between the two partners, mm-hmm. They are exploring different types of vocalizations within the vocalization space.
Yes, that is the idea, that they're exploring and searching for vocalizations that would generate higher degrees of social responding.
So you see different phonemes?
We haven't explored it at least in this study, we have not explored it at the phoneme level. We do have a partner who's looking at that sort of analysis with neural networks and things like that, but I'm not working on that.
Super interesting.
Yeah, well, we're resubmitting our revised paper next week, so if you think this is cool, please look up for that.
Okay, thank you very much. I think it's time for us to move on to Adria, who is actually already unmuted. So our next speaker is Adria Leboeuf from University of Freiburg, and she's going to tell us about socially exchanged fluid in insects.
Wait, I just want to interrupt with one thing, just to make sure that everybody stays around for the talk afterwards, which was in addition to the schedule. So we have 2 talks remaining. Just don't run away. Mm-hmm.
All right. Can you hear me?
Yes.
Good? We ready to go? So, great. Thank you guys for turning this into an online session. It's been super fascinating to hear about everybody's work. So many of us are interested in social interactions and social life. And I myself come from a more evolutionary direction, and in particular, how evolution manages to engineer social life.
So, you have a weird screen